All right. Hey, everyone. Welcome back to my living room. Thanks, everybody, for joining us today. Normally this is the Earth and Atmospheric Sciences Department's Planetary Science and Astrobiology seminar, but in celebration of Titan Week and our CSTAR distinguished lecturer who's here with us, Dr. Zibby Turtle, we thought that to kind of say goodbye to the semester, we'd have a really exciting panel today celebrating Dragonfly. We're thrilled to have with us 4 members of the Dragonfly team. If you were on last night's lecture, you've already met Dr. Zibby Turtle, but we're going to go ahead and go around and let our panelists introduce themselves, what they do on the mission, and give a little bit of background. And then we'll just open the floor up and have a great discussion for the next hour, hour and a half as we have it. So thanks very much. We can start with we'll start things off with Dr. Elizabeth Turtle.
Thanks, Brittany. I'm going to put up a slide here. We each made a bit of an introductory slide. Yeah. So I'm Zibby Turtle at the Applied Physics Laboratory, and I'm the principal investigator of Dragonfly. My background is primarily planetary geology, impact cratering, studying outer planet satellites in particular, as well as studying Titan's weather. In terms of planetary exploration, a combination of remote sensing and geophysical modeling. So I've worked with the Europa Clipper mission. I'm the principal investigator for the Europa imaging system for that. That's in development right now. I've also worked with the Cassini mission, the Lunar Reconnaissance Orbiter mission, and the Galileo mission. And for Dragonfly, as principal investigator, my primary role is to make sure that everything comes together so that we can achieve our science goals of understanding Titan's prebiotic chemistry, and the habitability of the Titan environment. And so that's my focus, is to look at the entire mission and make sure everything is coming together so that we can meet our. I can turn it over to one of our deputy PIs, Melissa Traynor, to introduce herself.
Hi, everybody. Give me 1 second to make sure I can do the screen sharing. Okay, can you guys see my slide?
Yes.
Great. So as I mentioned, I'm Melissa Traynor. I'm at NASA Goddard Space Flight Center. And here's a picture of me, I think the day after the Dragonfly site visit. Feeling calmer and a little relieved. So as Zibby mentioned, one of my roles is as one of the deputy PIs on the mission. I'm working with Zibby and the other deputy PIs, Jason Barnes at University of Idaho, as well as the rest of the science and engineering team, to make sure that Dragonfly can meet its science goals. I'm also the lead for the Dragonfly Mass Spectrometer, or DRAMS, which is one of the instruments on the Dragonfly payload. My background is in planetary atmospheric chemistry with a focus on organic synthesis. So I've spent many years doing laboratory studies looking at the synthesis of organic aerosol analogs, such as those that might represent the haze particles and particles that are formed in Titan's atmosphere, as well as drawing parallels between that and what may have occurred on the Earth billions of years ago. And I also, in those studies, I've used a variety of techniques, but my main specialty is with mass spectrometry, hence my role with the Dragonfly Mass Spectrometer. Some experience that I've had, I'm on the MSL SAM science team, looking primarily at in situ studies of the Mars atmosphere and atmospheric composition. So I've studied Mars atmospheres. I'm also very interested in Venus atmosphere. It's been 40 years since we've been in the Venus atmosphere, and hoping someday to get more measurements from there. So one of my big focuses in terms of the measurements that Dragonfly will make, as well as in the development phase that we're in right now, from the engineering side, is with the surface sampling. part of the Dragonfly mission. So this is the Dragonfly Mass Spectrometer, or DRAMS, and the drill for acquisition of complex organics, or DRACO. When you put these together, they comprise the in situ sample, measure the composition, the molecular composition, the Titan surface, and to do so in different environments. So to do that, we have our DRAMS mass spectrometer that uses a variety of measurement modes to look at the chemical composition of surface samples that the DRACO drills and delivers to us. And we're able to look at a wide mass range compared to, for example, the SAM instrument that has flown before. And we also have the capability to look for potential biosignatures, such as the chirality of molecules. If we're able to discover amino acids, for example, on Titan, we can look and see if there's an enantiomeric preference. So right now, much of my attention is spent on working on the development of the instrument to make sure that we meet all the science. So I think with that, I'll pass it along. I don't know if did I stop sharing? Yes. Okay. All right. So maybe since we're talking about instruments, I'll hand things off to Kristen.
All right. Thank you. And apologies. I actually have to ask how to share my screen. I've never used BlueJeans before.
There should be sharing options on the side of your screen or at the bottom.
It's on the right. Kristen, do you see the?
It's on the.
Doug, do you wanna jump in while I find the button?
I can.
Yeah.
It's the, just so you know, it's the one that looks like a little picture. It's the third one up from the bottom on the right. You can.
Okay.
And you just. Okay. Why don't you go ahead then, Kristen?
Okay. Okay, can you see my screen?
Mm-hmm.
Okay, so I'm Kristen Thompson. I am the Deputy Payload Systems Engineer, as well as the Instrument Scientist and the Systems Engineer for the Dragonfly Geophysics and Meteorology Package, or DRAGMET. So I have been working on helping to develop the engineering plans and the requirements for the DRAGMET instrument, and also trying to help shepherd the other instruments through the systems engineering process, so requirements development and interface development, instrument operations, and that kind of thing. So I've historically been a space systems analyst, and started moving into systems engineering with the Deep Space Advanced Radar concept as the mission systems engineer, and then for Europa Clipper, I worked on payload accommodations as part of the payload systems engineering team. But I'm also finishing up my PhD in planetary science, and I've been focusing on planetary atmospheric spectroscopy and atmospheric processes. Which is why I've been working on the DRAGMET instrument. So the DRAGMET payload, just a quick overview. Melissa already mentioned DRAMS and DRACO, the mass spectrometer, and the drill for acquisition of complex organics, and those two work together to do the higher resolution mass spectrometry for Dragonfly. And then we also have DRAGONS, the gamma ray neutron spectrometer, which gives us more a look at the bulk composition of the surface and near subsurface at the landing sites. And then we have the geophysics and meteorology package, which I mentioned, which is looking at atmospheric processes and properties like temperature and pressure and hydrogen abundance and methane abundance and humidity to examine the methane cycle. And we also have some geophones and a seismometer, so we can listen for Titan quakes and subsurface activity, as well as measure surface properties the soil at the landing sites. And then we also have DragonCam, which is a camera suite that includes panoramic cameras, which are the ones on the high gain antenna here, as well as cameras that examine the surface in front of and underneath the lander, and microscopic cameras that really focus in on the drilling sites so that we can get a good visual of what we're actually drilling and collecting and sending to DRAMS and Draco. And so for the systems engineering roles, the systems engineers really focus on making sure that everything is connected properly and that we're meeting all of the science requirements, and looking at performing all the integration and testing, as well as operations design for the instruments to make sure that we can, that when we get to Titan, we can perform the science and achieve our science goals and objectives, and also return all the data, and that everything is working properly, so that we can get as much data and as much valuable science as possible out of the mission. And with that, I think I'll hand it over to Doug.
All right. So I will do the same. I'll share a little brief background about myself. I hope this is coming through. It says it is. So the left is a photo taken at our first team meeting after the win, and that was a lot of fun. And we were very excited to win Dragonfly. We forget that it was a competed mission, and that was a large part of our lives for a number of years. So I'm Doug Adams. I am the Dragonfly flight system engineer. I also noted that, I architect and chief engineer. So one of my chief responsibilities is to put together a system, a flight system, an engineering system that will achieve all of the science objectives that Zibby, Melissa, and Kristen have discussed. And that includes accommodating the science instruments, but also executing the science mission, both getting to Titan and then on the surface of Titan. So my background, I spent 12 years at JPL, and then the subsequent 8 have been at APL. And I principally worked on planetary landers, but I also worked on a couple other spacecraft, a number of the deep space exploration robotic spacecraft. A lot of what I did was in the EDL world, the entry, descent, and landing technologies, and that's where I got to apply. I was a little bit fortunate in how things came together. I got my PhD in applied mechanics and dynamics, and that was kind of just a natural place for me to settle out, and I've had a good career doing it. So some of the things I've worked on, I cut my teeth on the MER program, Spirit and Opportunity rovers, that had a long life on Mars. Moved from there to the Phoenix lander. I was the EDL mechanical systems in for Phoenix. Followed that with being the role of cognizant engineer for the parachute on the Curiosity rover that is still driving around on Mars today. Did a stint as the Balut cognizant engineer for the LDSD program, which is an interesting problem if you want to talk about that. And I was also the dynamics lead for SMAP, which was Earth orbiting platform, a very challenging dynamics problem we had there. The only thing, I'll just throw this up. Zibby talked about this last night, and you've seen some of this material from Melissa and Kristen as well. But this is, if you will, this is the flight system. The flight system is that which flies in space. And we have to get to Titan, so we launch on a rocket, of course, and we have a cruise. It depends on the launch vehicle that we get, but it takes us something on the order of 8 years to get to Titan, again, depending on the rocket. We're spin stabilized. That's why you see the circular cruise stage and the axisymmetric body. So we have oblate inertia properties in space, very much like MSL and now the Mars 2020, the Perseverance rover that's on its way to Mars is going to land in February. They're also spin balanced. We do hypersonic atmospheric entry, descent and landing. It takes us about 2.5 hours to get down through the atmosphere. And then on the surface, we do a transition to powered flight. And what you see on the right is our lander. It's an X8 configuration. So we say that because it has 8 rotors as opposed to an octagon configuration for the 8. It's a rectangular configuration for the 8, and they're stacked. That's for redundancy. So if we lose one, we can keep flying with the other 7. And the only other thing I'll mention real quick is that, actually, I guess 2 things. One is that this is big. This is not a daughter craft or something. It's approximately 12 feet wide and again, about 12 feet long and about 5 feet high. And the thing you see on the back, that cylinder you see on the back houses an MMRTG, which is our proposed power source that is the same power source that is used for MSL and the Mars 2020 Perseverance rover. We use it, though, to keep ourselves warm in the 94 Kelvin or minus 179 C atmosphere of Titan. And I think with that, I'll just stop because we can go to other Q&A. So thanks, and take it away, Brittany.
Yeah, that was really great. Thanks so much for the introduction, folks. So I'll turn it over. So just a reminder to everyone watching, there's a chat. We've got a poll that's going. We've asked if the Dragonfly suit that Doug was just showing himself wearing is the best that you've ever seen, or whether you've already ordered it from Amazon and not sponsored by Amazon in any way. And then let's have some questions. So the students from the class are they are able to ask questions. So, and then if there's anyone who's an attendee and wants to ask a question, just post it in the Q&A section down at the bottom. So with that, let's go to, folks who are presenters, if you just want to raise your hand or unmute and ask a question, that would be great. So have at it.
I will take the first question if no one minds.
Nice, go for it, Chase.
So, Dr. Turtle, you mentioned last night about the sampling system, how you're going to have to take into account, obviously, what kind of things you're going to sample, as in this organic sand. I'm curious of what kind of analogs you're considering, maybe more specifics if you have them, but also like what we expect them to be. Do we expect them to be kind of like sticky or something that might sort of gum up the works of the sampling system?
Yeah, so that's exactly what we need to pay attention to. Could things be sticky and not so much the system, but be stuck in the system so that you measure the same material and you get to a new landing site and you're sampling new material, but you still have some of the old material in there, and so that's one of the things that that Melissa needs to pay attention to in terms of the contamination control and how we make sure we understand which materials come from which part of the surface. So we want to make sure we don't have things that get stuck inside the system, as you say. So there are a number of different things that can be used as good analogs. One of the materials that's been used is sand and oil mixed together because that's definitely sticky, and they did a lot of testing of the sampling system and the opening into the pneumatic system and then the system itself. Another analog that's been used is crushed walnut shells, actually, and they've just been using that actually the last couple of weeks here at APL in our new test facility that matches aspects of the Titan environment. So there are a wide variety of materials. We have, I can't remember the number, maybe you do, the Draco team tested in phase A, but we have this big matrix of like 20 different types of materials and combinations to look exactly at that kind of thing. What's the most effective sampling system to get the material in, and then how do we make sure we don't have cross-contamination, et cetera.
Hi, my name is Ashley Hanna. Thank you so much for having this panel. My question is geared towards the mass spec, and I kind of wanted to know what your thoughts were on why you chose the mass range. Why did you decide to go with two modes of analysis, so LDMS and GC, and then also as a follow-up, your GC is able to do chiral analysis, and I kind of wanted to know about how you plan on doing that.
Okay, so I'm going to make sure I answer all these questions. Why mass spec? Why two modes? How do we do chiral? So for the first question, what we wanted to do when we were planning the mission is to take hardware instrumentation that's been proven out in other environments and other planetary exploration and then adapt it to go to Titan, right? We didn't want to pick a completely brand new, untested type of instrumentation because we're sending a drone to Titan and there's plenty of other challenges in there, right? So we wanted to kind of build on work that's already been done with the mass spectrometer, spaceflight mass spectrometer community. So the mass spec that we're using, it's an ion trap mass spectrometer, and it's based off of two instruments that have been developed for flight for Mars. So one is the Mars Organic Molecule Analyzer, or MOMA, and that's actually, it's been fully qualified and it's ready to fly on the ExoMars rover, which is getting launched in 2022. And we also have a lot of heritage, though, coming out of the Sample Analysis at Mars, or SAM instrument that's on MSL and has been operating on MSL for years and years. What is the two modes that I mentioned and that you asked about are unique in particular to the MOMA architecture, which is the ion trap. And the reason we wanted to choose that is because we know that Titan is going to have diverse types of surface materials. We're looking at, for example, we talked a little bit about the organic sands that we expect to measure. We think these are really complex organic molecules based on what we understand from measurements at Titan, as well as the types of laboratory simulations that are done. We expect them to range in very high molecular weights. And the laser desorption mass spec mode in particular is very good at looking at high molecular weight compounds, because you're not relying on them having volatility necessarily. You're using the energy of the laser. You just put the sample right in front, you shoot it with the laser, and you have this combination desorption ionization step that can turn even very large molecules into ions that focus into the mass spec and then be able to measure them. And so that laser desorption capability allows us to look at sort of higher molecular weight compounds that we think we're going to find there, just based on everything we know about Titan chemistry. And it also lets us do that with sort of what I would call like minimal processing of the sample. We don't have to heat it. We don't have to do other sample processing things. We do have to collect it and deliver it in front of the mass spec, and then the laser probe the surface. So that's why we want that mode, but then we wanted to be able to do an additional sort of separation step and a little bit more selective measurements. And in a way that has been done, again, previously on other missions that have been looking for organic compounds. And so that's where the gas chromatography mode comes in, or GC. And that allows us to add that additional step, and the molecules go through the GC, they travel through, and they get separated out based on size and chemical functionality before going into the mass spec. And so it helps us kind of take what we expect to be a complex mixture and sort of sort everything out in a way where we can do a really definitive identification of some of the molecules that are going to be found in the surface. And so with those two complementary modes, it really helps us kind of get at all the aspects of the composition that we're at Titan. The way the chiral measurement works is that we have a column that is, it has what's called the stationary phase that coats the column, is able to separate out enantiomers. So for example, for different amino acids, as I mentioned, that is one of our target molecules, the column has the ability to separate out the left and right-handed molecules from each other, just based on the interactions with the stationary phase. So we find amino acids on Titan's surface using the GC mode, the first step we have is called derivatization. This is something that helps change the chemical functionality of the molecules to liberate them so that they can get into the gas flow. So they sort of increase their volatility. And then they go through the chiral column and they get separated out. And then we can see if you have a lot more left-handed or a lot more right-handed, or if they're approximately equal, which is what we expect to find in abiotic systems. All right, I talked a lot, but I think I hit all three of your questions, Ashley.
Yes, that was great. I guess my last follow-up really quickly is, do you have any fears about decomposition through the pyrolysis of those like amino acids, like larger amino acids?
Yeah, so the amino acids I'm not as concerned, because that's the derivatization step that we use is really optimized to prevent that kind of decomposition. So most of our GC cups will have this like preloaded chemical reagent in a little capsule, and once it gets to a certain temperature in the oven, it opens up, mixes the derivatization agent with the amino acids, and it replaces some of the functional groups. As I said, that makes it a lot easier for them to get into the gas flow. So this is something that's been done. It's done commonly in the laboratory. It's on the SAM instrument, and it's also going on the MOMA instrument. So this is something that has been sort of proven out as a good approach.
Thank you so much.
Okay, thanks.
I'll take a second here just to ask a question that I thought was great from the Q&A. So let me just get that open. And it was, let's see, it was actually one of Josh Doulet's questions. And it was about the pipeline. My daily robotic work uses computer vision for pose estimation and localization. Can you explain a little bit about the perception pipeline and methods or algorithms that will be used to estimate pose and localize Dragonfly? Wondering if it works with feature detection or something more experimental.
So I'll ask a question. When he says pose, I'm not 100% certain I understand what the question is. Is this about optical navigation?
Vehicle attitude, basically. Like, how are you controlling for? I know everyone uses slightly different terms depending on what field you work in. So the idea is, with underwater robotic systems is what is one of the ways that we use it, where you try to look at the changing perspective on a feature to estimate how your vehicle is positioned. And so we were just wondering how does Dragonfly control attitude or know that it's got the right attitude? Does it use anything that's visual?
Okay, yeah, sure. Now I understand. Thank you for the explanation. Yeah, as a matter of fact, we have a number of sensors, and I don't have my slide handy that talks through all of them, but I'll just mention briefly the way this comes together. So we have an extended Kalman filter that we use to propagate our navigated knowledge, both position and state vector of the vehicle. And we use optical navigation, optical odometry, really, to establish our relative position as we move across the surface, and also to find our way back. We use a technique we call breadcrumbs, where we store images that we wish to read in order to retrace our steps. Regarding the attitude of the vehicle specifically, though, that's tracked with an IMU. We integrate the orientation of the vehicle with an IMU. We actually use a Honeywell MIMU, which is a very precise scientific grade IMU. The interesting part that I'll add to that, though, is that we don't have a really good way of initializing the IMU once we're on the surface, because from Titan's surface you can't see the stars. You can barely see the sun. It kind of shows up as a big blob in the sky due to the diffusivity of the atmosphere. So what we have to do is we have to do a kind of an approximate local estimate of our initial attitude, where we do a gyro compass before we take off to estimate where north is, and of course we can sense gravity with the accelerometers, and we use that as an initial state. But the question's very good, because in fact what we do is, as soon as we take off from the ground, we start to use the previous images we took, and in fact the image-to-image sequences as we take off from the ground, to correct for yaw errors, because it's very difficult. There's no magnetic field on Titan, so we don't know where north is, and we have to be able to remove the yaw error in order to establish our ability to retrace those breadcrumbs that I mentioned earlier. So in fact, we do use optical techniques both for initialization of our state or correction of the initialization of the state, and for our navigation on the surface. And I think that answers the question, but if I missed it, please let me know.
That's great. It's actually, I wanted to ask that too, because it is the same problem that we have when we do under ice work. So we put a robot with an IMU initial that wants to be horizontal, but we have to get it vertical to go through the ice. When you get out underneath, then it's anybody's best guess. Plus, we're at the South Pole, where the magnetic field is, shall we say, not particularly cooperative. So that made me really excited that we're basically navigating on Titan. So that's really exciting.
Yeah, I would say it's very similar based on your description. Yes.
That's cool.
Hi all. I had a tangentially related navigation question. When you're in flight, does any of the science data or is any of the instrumentation active in terms of selecting the next landing site, or is all sort of pre-selected based on engineering safety?
So I'm going to let Zibby give an answer too, but I'll give you a quick one, which is we have dedicated engineering cameras, nav cams. There are 2 of them. And those are used, they're panchromatic cameras that are used specifically for their ability to take high shutter speed, sharp images that we can use for navigation. And we use those cameras to survey future landing sites. There's a leapfrog technique that I could get into. I think Zibby may have talked about that yesterday. But the nav cams are our primary source of information for scouting future landing sites, for inspecting future potential landing sites. However, we do take science images when we fly. We use both the forward and down cameras at different points when we're flying. And maybe Zibby, if you want to comment on that, please feel free.
Sure. Yeah. So we'll take measurements in flight and we'll take images as we're flying. We'll actually initially just play back thumbnails, but we'll keep the data on board so that we can select any particularly interesting images to play back at higher resolution. But yeah, as Doug says, we have this leapfrog strategy where we actually go out and scout future landing sites before we come back to a previously scouted landing site. And this allows us to look ahead both, as you say, from avoidance perspective and landing site safety perspective, but also to do imaging with the various cameras to look ahead at the potential landing sites in terms of the scientific opportunities that we may have at those landing sites. In particular, what we will do is identify, we'll scout a landing zone, which is a bigger area than the lander itself. And then we will target, within that zone, we will target specific areas of interest as target landing sites. But ultimately, the determination of the safe landing site and the best place to land is left up to Dragonfly, which does that autonomously. So we will provide the guidance based on what we see, and then Dragonfly will select the best place within the landing zone that we target.
I'll just jump in real quick and add that we will also have some of the Dragnet sensors active while we're flying so that we can collect data on the temperature profiles and methane humidity profiles and that kind of thing. It's not relevant exactly to the mobility system, but it is still science data that we'll be collecting in flight.
And I'll add to what Kristen said, which is one of our science requirements is to be able to do atmospheric profiles. We have to fly to from the surface to 3.5 kilometers above the surface to do the same using the DragMet sensors. So we don't talk about that a lot, but that's one of our key requirements as well.
That's great. Thank you.
I had a question for, and anybody could answer this. I think Zibby kind of answered this yesterday, but I was interested in learning how you guys, basically like how you got to where you are today, and any advice you could give grad students, and basically how you got the opportunity to work on this mission.
So since I spoke to that last night, I'd like to defer right now to others. I'm happy to provide more information, but in the interest of time, I'd like to let others speak as well.
I'll just jump in real quick, but also I'm sure Kristen and Doug can add. For me, it wasn't necessarily a planned path to get to be a scientist at NASA. I, probably like many of you, I liked science and math in school, so I kept doing it as long as they let me, pretty much. Went to grad school because I wanted to keep going to school because I loved learning and loved the research environment, and was looking around for projects in graduate school, found atmospheric chemistry very interesting, and then it turned out the project that was available was planetary atmospheric chemistry, studying Titan, and that's when I fell in love with Titan and early Earth, and a lot of the way that I describe my career path is kind of saying yes to things that you didn't necessarily expect as opportunities, but they come along and you take the chance. So after doing my graduate research and finishing my PhD, and I've started a postdoc, this job opportunity at Goddard came along to work in a group that makes mass spectrometers. I had used mass spectrometers in my research, but I didn't necessarily know how to build them. But they were looking for scientists, who are using mass specs for planetary research. And I had didn't know much about the job. I had been planning to do something totally different with my career, faculty jobs. But I said, well, sure, let me check it out, let me visit it, and ended up joining the group at Goddard. And from there, I was lucky enough to be in an environment where mission support is a big part. And so that has exposed me to a lot of opportunities that I may not have necessarily had if I had stayed in sort of a research only focused opportunity. And so then being kind of where I am, I started working with Zibby back on the Titan Mare Explorer time many years ago, previous proposal, and I think I even saw some Q&A about that. And then usually once you start to meet people and you work with them, you find groups of people that are really good to work with to help you accomplish kind of some of the goals that you have in science and in exploration. And I find that a lot of mission work, you end up seeking out the people that you know are good team members, are good teammates, do the best work, but also are good to work with. So I don't know how helpful of an answer that was, so I'm going to let Kristen and Doug chime in too.
You go ahead, Kristen.
So I think I'll echo a couple of things that Melissa said. Completely agree with being open to opportunities that maybe you didn't think were on your career path, but if it's an opportunity to work with a really cool concept, or even with a really good team, those can be good things to follow up on. I will say that I speak from personal experience, and that one needs to be a little careful about saying yes to everything, because that can and I notice all three of our other presenters are nodding their heads. But yeah, because that can lead to burnout, but it can also lead to a lot of really cool opportunities. So, and for me in particular, I had the opportunity to work on the Titan Mare Explorer back many moons ago, primarily with Ralph Lorenz, who is the mission architect for Dragonfly. And then built on my my systems engineering experience with a couple other mission concepts, and particularly with Europa Clipper. And so working with the instruments and learning about how they work and how they interface to the spacecraft and what the different needs are. And so when Dragonfly was looking for payload systems engineers, I was well positioned because of those roles, and also because I'm been working on my PhD in planetary science. Having the science background and the engineering background is a good combination for the systems engineering, because those are the people who have to kind of translate between the science and the engineering and make sure that, and try to keep both sides happy as much as we can. So.
All right, so I'll go last, and unsurprisingly, and I'll try to minimize the repetition, but unsurprisingly, you'll see some common threads as well. I'll go back just a little bit to, I co-opted Johnson Space Center as an undergrad and master's student. I think I even did a tour before the start of my PhD program. So I always kind of thought I would do manned spaceflight stuff. But then I was in school, I was in school for a long time doing a PhD program. And when it came time to get out, I kind of surveyed what my options were. And I liked space. I wanted to do something in space. And, they were staffing for the Mars exploration rovers at the time. And they recruited me to come to JPL and work on that. And like Melissa said, and echoed by Kristen, I had never really thought that much. Again, I had kind of a manned spacecraft background. I thought, well, okay, let's do it. Let's see what happens. And it turned out to be a marvelous experience. It was kind of the spark. Everything just kind of blew up from there. It was the perfect fit. And then as I had mentioned earlier, I had this kind of series of missions that just kind of went back to back to back, and one kind of fed into the other. And but then to get to Dragonfly, though, we made a family move to the East Coast, and I joined APL. And when I did that, I made a conscious decision. I had always worked on the missions, and this time I wanted to be one of the people that was developing or kind of architecting. I use the word architecting the mission so that I could solve the problems before they became problems. And so I kind of made that career switch when I came to APL, and I started doing a lot of proposal work. I worked on a number of proposals, Discovery and New Frontiers proposals, which is something I never really thought I would do, but it turned out I really liked that because it gave me the application for all this knowledge that I'd kind of accumulated. And then one day, and I'll use Ralph's name again, it was mentioned earlier, I was called into an office, and Ralph sat on one side of the table, and Ken and I sat there with Cheryl Reed, and so we had this kind of crazy idea. We want to put this octocopter on Titan, or actually they said quadcopter at the time, and we all kind of looked around at the table and said, well, we think we can do it. And here we are today. It was a Herculean task. I cannot understate, or cannot overstate, that is, how much work we put into it. It was a work to exhaustion experience. But that's the path. As I didn't expect to be in robotic space when I was in school, and then I ended up there. And I, like Melissa said, I kind of just followed the opportunities as they came along. And Dragonfly, we had lightning in a bottle with that one, and so we all put our shoulder into it, and we're here talking today.
Thank you all for answering that. That was awesome.
I'll quickly ask a question that's been on there for a while. So this is from Aaron Patel. I'm curious about the organic sand on Titan. Is there a danger of any electrically isolated building up charge during flights, or electrostatically collecting airborne material? And is there a means of grounding it or clearing anything or any accretion on the vehicle or on camera lenses or something like that?
Who wants to take that one?
I was going to tell Kristen.
Doug, I can start. And
Okay,
then
go,
maybe,
Chris.
Doug, do you want to finish it? Okay, so I'll talk from the payload perspective, and then Doug can speak to the lander perspective. So we do have, that is something that we have been thinking about, and we do have requirements for the instruments to be able to mitigate the impact of accreted material and airborne dust and that kind of thing. It is something that we have been thinking about a lot for the camera lenses in particular, and we have a trade study going for that to figure out the best way to either prevent accretion or remove it. Interestingly, we actually have one of the instruments on Dragnet is it's an electric field antenna that is going to be looking to measure the change in the electric field and the charge buildup when the rotors are blowing, actually. So it is something we're thinking about, and it's actually something we hope to measure as well as mitigate detrimental effects. And the instruments have to be grounded to the lander, and then the lander I'm sure has a grounding scheme to make sure that that there's no rapid charge dissipation. So I'll let Doug speak to that if he wants to.
I'll comment just briefly on it. We were aware of the risk of static charge when we, even in the proposal phase, to the point where we described having, if you've flown on planes and never noticed, you'll see these little fingers kind of sticking out near the wing tips on the trailing edge of the wing. Those are static wicks that are designed to bleed off static charge in the same way that a lightning rod would here on Earth. We went so far as to even include static wicks on the rotors and on the body of the lander. The interesting thing about that, though, is because there's no water in the atmosphere, there's no ions, so you actually have to bring your own ion supply. And we discussed whether or not there are merits in doing that. And to be honest, right now, we don't have a fully architected solution for exactly what we think we're going to fly to mitigate that. But having said that, as Kristen described, we do currently plan to have the entire exoskeleton of the lander be a conductive surface, so that you don't have some big static buildup in some place that could arc and cause a problem. We are keenly aware of the risks of building up a static charge, and we are planning to have grounding straps and measures in place to mitigate that. Kristen, I think we stunned them into silence. I'm not hearing anything.
I'll ask a quick question. Is the direct-to-earth telecom system X-band, KA, or both?
Yeah, that's a quick one to answer. It's a X-band. We have a 100-watt X-band transmitter. We considered KA. There are a couple reasons we didn't fly that. One is that we don't really have the mass and volume to accommodate two different bandwidths. The antennas are very different. At least it's challenging to do dual band X and KA. It can be done, but we needed to avoid complications. So the other thing is X-band transmits through the Titan atmosphere in a rather happy way. So it simplifies our overall, because you really, KA is designed for downlink only, and you need X-band for uplink. So it's much simpler for us to have a single band, and we use X-band is the answer.
Okay, great. Question about the development. For Dragonfly mission development timescale, how did the Titan Mare Explorer and other proposed missions influence Dragonfly's development? And is there anything that you wish you could have included on Dragonfly that had to be cut?
Let's see. I can certainly speak to part of that. There are a lot of aspects of the Titan environment and planning for exploration of the Titan environment that had been developed as part of the Titan Mare Explorer proposal that we could leverage into the design and the environmental assessments for Dragonfly. Obviously, the Titan Mare Explorer, which was designed to send a probe to float on one of the northern seas at Titan, has a substantial number of differences as well. But in terms of entering the atmosphere, in terms of functioning on the surface at 94 Kelvin, there were a lot of aspects of that that we were able to take advantage of. And I'm sure Melissa can speak more specifically to some of the work that was done related to the mass spectrometer. Very quickly related to, are there things we wish we could take with us that we are not? There are always things one can think of adding to, adding to a mission. There are always different instruments or capabilities that one would like to add. I think we have a good solid set of complementary measurements, and so I'm trying to keep focused on that, making sure everything that we have continues to fit together and work within the resources we have. But I'm sure each of us could list a number of things we'd like to add as well. Melissa, I don't know if there's anything specific to the mass spectrometer from the evolution of that.
Yeah. I mean, what we have on Dragonfly has ended up being quite different than the mass spec that we were thinking of for time. Partly because with time, what the goal was to ingest the sea sample and make a quantitative measurement of the relative proportions of things like methane, ethane, propane, and some of the trace compounds. But we had this really big technology development effort to develop what that inlet would be. So you're trying to think of, how do I design an inlet that can safely ingest a 90 Kelvin liquid, but then encapsulate it and then heat it up to much higher temperatures and send it to an instrument. So what I would say is there's a lot of learning that we did there relative to materials, relative to thinking how to function with these gigantic temperature gradients and these big temperature swings, kind of, and how that can all couple from an environment into the instrument that has to be held at a particular pressure to operate properly, things like that. So there's a lot that we learned in that process. That's why it's not directly relevant. We don't have that liquid inlet, we have a very different surface sampling system for solids, but a lot of that work translated. So, and a lot of some of the people who worked on that particular project, like some of the cryogenic engineers, are the same cryogenic engineers that are helping us now figure out how do we keep our sample cold while we do LDMS on it. So a lot of times what happens too is just the people help carry you into challenge.
I have a question. I'm Chinmay. I work on impactor missions to icy worlds. So I think that was a really good place for me to ask my question. How straightforward is the technology transfer from Dragonfly to something like Europa or Enceladus flyby or a lander mission? Of course, I understand that the sample collection is going to be different, but what about the analytical instrumentation transfer-wise?
I'll take a short answer at that and then see if anyone to talk about it. There's a lot that's in common. There's a lot of developments that are happening all sort of in parallel. So at the same time that we were putting together a concept for DRAMS, for the Dragonfly mass spectrometer, we had in our group another effort looking at how to develop mass spectrometers for Europa lander, for example. In fact, Will Brinkerhoff, who is the deputy lead on DRAMS and a co-I on Dragonfly, is the PI of an effort to develop a similar mass spectrometer with some differences, though, that can operate on the surface of Europa. So there's some parallels there in thinking through how you do the automated GC or LDMS on samples that might have, for example, an ice component or come from a very cold environment. But then there's also going to be big differences, right? So the big challenge on Europa for a lot of what we're trying to do is the radiation environment and thinking that through, as well as maybe power limitations and time. You have to operate much quicker before you perish. The big challenge in Titan, one of the big challenges is, in addition to the temperature, we also have this big atmosphere, which is, for a mass spectrometer, something you want to usually get rid of when you're doing your measurement inside the sensor. And so it's every time we do a new development, every time we're able to prove out hardware that can work, it absolutely can transfer to other environments. But then the fun of it is not just every target we go to, but every architecture change ends up being unique, right? And so that's where all the fun comes in, and that's why this work is so super customized. Every instrument's a little different, at least for the kind of stuff I do.
Awesome, thank you.
There was a question that also came up last night, but it was we talked a little bit about EDL. But one of the questions was, why is it a direct Titan insertion instead of using something like Saturn aero capture, aero braking, or something like that?
Yeah, so it's interesting to think about how you could do it. You could even do an aero capture and then entry at Titan as well. Of course, you could hit the atmosphere there. The harsh reality is that it comes down to costs. We just don't have the money in the budget for a competed mission to do anything more than we must when it comes to technologies. You have to remember, EDL is a means to an end. It's how we get to the surface. It's not actually the science mission. So we have to achieve that as efficiently as possible. And a direct entry is extremely efficient. You hit the atmosphere, it makes good use of the ablative materials, and it gets you down to the surface with minimum hardware and minimum effort to do. So that's the real reason why we don't do something. Because you could imagine you could use one of these deployables or something to have a very low ballistic coefficient entry that would be very low G. And yes, it could be done, but those are additional complications that we just can't afford, which actually I'm going to use that briefly for a quick segue to what we wish we had. One thing that would be super nice, which also violated the cost problem, it would really be nice to have an orbiting asset that we could transmit data up to relay to Earth. In fact, I actually went so far as to even sketch up in PowerPoint what it might look like to launch something like that. And we showed it at a meeting in West 202, and we all looked at it, and every single one of us said, yeah, that's flagship. We can't do that. So it made it to the cutting room floor pretty quickly. But that's an example, not unlike the EDL question, where you just have to make choices to fit within the box.
So Catherine, sorry, go ahead.
Sorry, Brittany. I had a follow-up question on that data transfer issue. That seems to be common across a lot of missions in a Europa lander. A CT team also had some challenges and scope issues with an orbital data relay. Is there a long-term solution for that, or are people working on a way of easing that problem? This is a little bit more general, but it seems like Dragonfly also had that problem.
I'll give you a quick answer. The quick answer is that we would all very much like the Deep Space Network to keep the 70-meter assets in play, because having those 70-meter apertures makes a huge difference in terms of being able to downlink data. Arraying 34s can duplicate that, but then you're committing the whole complex assets for what one aperture could do. So that's thing one, is to have a good Earth aperture. In situ, though, it becomes a case-by-case basis. For Europa, I also worked the Europa lander. I was on the Europa lander team at APL, and the original plan was to leave the carrier spacecraft in orbit to act as a relay. Of course, at Europa, the problem there is the radiation environment is so intense that you can't expect anything to last long on the surface or in orbit. Titan would be different. You could have something that could last a long time there, but it would be very specific again to the mission. You know, there aren't that many missions at Titan. It's an outer planet. It's hard to get to. So Mars is unique because it's very close, very relatively straightforward to get to, and there are a lot of orbiting assets. So I think that I'll leave it at that. I think the challenge is the mission-specific challenge. But again, from a NASA support perspective, the bigger the aperture, the better for downlink.
So Catherine Udell, I know you had a question. Did you want to ask yours?
Yeah. I was wondering about the seismometers and what you guys might expect to find and what you think might cause what you find.
So I can start this one off, and then if Zibby wants to fill in, we can do that. So we want to take some seismometers to Titan because we actually don't really know what the internal structure of not just Titan but most icy bodies looks like. So we want to, and we think that the main source of seismic activity on Titan would be tidal forces from Saturn. But since we don't know what the internal structure of Titan looks like, we don't know exactly what that tidal forcing, what the effects of it would be. So if we want to take the seismometers so that we can listen for seismic activity, how often do we see signals and how strong are they? And that will give us an idea of, or at least start to give us an idea of what the internal structure of Titan might look like, and whether where there might be like a subsurface ocean and how deep it might be, and that kind of thing.
There's a few more questions, but I'd like for the students in the class to go ahead and ask another. So think about that for a second. There's a question from Sam Rappaport. What do you see? What is the limiting factor on mission lifetime?
So that one's pretty easy. Go ahead, Zibby, please. No, you go ahead. No, you go ahead. That's fine. You got it.
The MMRTG is the limiting factor. We rely not only on the MMRTG for power, of course, but we're relying on the heat from the MMRTG, and of course with the plutonium eventually put in terms of power and and heat from the MMRTG will not be able to keep us warm on the surface. So it depends a lot on some of the specific implementation and the timing, but the lifetime the limit on the lifetime from the MMRTG is likely to be several years. So we have margin on our nominal mission plan with that, of course, but that's ultimately what will limit the lifetime of Dragonfly on the surface of Titan.
Thank you.
And then, does Dragonfly have to land on flat surfaces, or does the suspension allow it to land stabilized, or to stabilize for drilling on uneven terrain? And does it have its own landing gear, analogous to the other, like the rover, like the Curiosity rocker system?
So that's a good question. The answer is that we carry a requirement, and this was something we thought was reasonable, that we be able to land on up to a 10-degree slope with quarter-meter tall, aka half-meter diameter hemispherical obstacles. Those obstacles can be above or below. You know, they can be depressions or they can be bulges on the surface. The question of sampling is interesting because we also have to support, and there are requirements we carry for the weight on bit for the drills. We have to the weight of the lander. Now, having low gravity is great for flying, right? You know, it makes it easy to get off the surface and fly. But then when you try to press on a drill bit, it's not so good because you don't weigh very much, and you can actually jack up the lander if you don't have enough weight on the bit to drill. So the drills are hammer drills, which help because, of course, you have an impulsive load for a very short period of time, very high force to help you dig into the ground. But the attitude of the lander, to the last question, or the last part of the question, is a player in that too, because if you have an uneven landing site, then that affects your ability to put weight on bit. You know, the left front drill, for instance, might be light, whereas the right front is heavy, and that'll be part of our landing site assessment when we decide which drill to use. The landing gear itself, the way we architected it in the concept study report, the big report that we submitted to NASA, was that the landing gear was articulated. So there are 4 pneumatic dampers. We didn't talk about this, but because we have to make at least 40 landings, we use a pneumatic system, a pneumatic damper system, to absorb impact when we land on the ground. We didn't want a rigid system because that could lead to very high loads when you land, because we don't really know for certain what we're going to land on. We would like to land on ice, for instance, which is very hard. Of course, as we've described, or Zibby's described, we plan to land in these sand dunes, these hydrocarbon sand dunes, which could be very soft. So we use this pneumatic damper system, to account for the uncertainty of the surface and the uncertainty in the topography of the surface. And again, they're articulated to handle that. So that's the plan. So it's sort of like what's on the Curiosity rover, that has a rocker bogie system that are coupled. So the 6 wheels it's a little complicated to describe over this medium, but the deal there is that it's architected to handle all sorts of terrain as it drives. We have a similar system in the sense that we have this articulation in our gear to account for the terrain uncertainty.
Let's see, checking on questions. I think we've covered most of these. Yeah, okay. Are there any more questions from the students in the class?
I maybe have a naive question. So during the presentation last night, Dr. Turtle mentioned that at nighttime, you may be able to detect organics by UV fluorescence. And I'm just kind of curious, if you can use UV fluorescence in a similar way that you could use like infrared spectroscopy to identify maybe what, other than maybe like the mass spec methods to identify the organics, could you use fluorescence to maybe cross-correlate that in some way, or are they just sort of all fluorescing in a similar way?
Different materials do fluoresce differently, and I could try to pull up the image, but you do see different colors from different materials. I don't know that it's unique enough to, in a way that would allow us to specifically identify individual materials based on, what we're seeing with the cameras. But by correlating that with the measurements that DRAMS makes of the surface materials, we might get we might be able to infer that if something glows kind of green, it's likely to be, what one of the materials that DRAM samples, or if it glows blue, it's likely to be another. So I think we'll be able to do some. Well, I'm optimistic that we'll be able to do some kind of high-level correlation, but I don't think it would be as diagnostic. We don't have the very high spectral resolution, and it may not be sufficient in that sense to actually identify them without ingesting materials into the mass spectrometer.
Great, thank you.
I have a maybe quick question. So you guys use gamma ray and neutron spectrometer to look at composition of the surface. I just was curious, and you may have already covered this, but is there a reason why you didn't use Raman to look at surface composition under the lander?
Do you want me to?
Yeah, if you want, Melissa, go ahead.
Sure. This question is it's a great question. It kind of goes back to the earlier question: is what do you wish you could include? What did you have to take off? We went through and considered a lot of different ideas when we were beginning to put the payload together, and Raman was one of the ones that we considered. But one of the reasons that we, for example, are using the approach with Dragons, the gamma ray neutron spectrometers, it really gives us an idea of this whole area around the lander. We get this immediate sense of what are we sitting on, and we get that sense shortly after landing. I mean, it takes a while to integrate, but we can do that shortly after land, and it's really helpful for us because we're trying to identify different geologic units in part on like a slightly larger scale than what you might observe with a small focused Raman. And so we get an idea of if we have layering, if we have a layer maybe over ice, or if we have ice that has a bunch of salt in it versus pure ice. And we get that for that area all around the lander where it is. And so that feeds in part into a lot of the other investigations in addition to just sort of that molecular surface composition investigation. And then we accomplish the molecular investigation with the mass spectrometer. But I mean, a Raman would be an excellent addition too, but it all comes back to hard choices and squeezing in a box.
Okay, thank you. Yeah, I have a follow-up question to that. Is the reason why you're looking under the lander, is that because you can't really look that far away with Dragons? Or I guess I just was curious as to why it's just focused on below the spacecraft.
Right. So the way the approach works in general is put out neutrons from the pulse neutron generator, and it interacts with basically the whole area around, and then you get the signal back from this radius around the lander. So it's not like a targeted approach where you can go really far away. So it's sort of about sensing the environment around where, a whole radius around the detectors. If that makes sense.
Yeah. Okay. Thank you. Thank you so much.
Last call on questions. Well, folks, this has just been fantastic. Thank you so much. I mean, we still have 44 people online, and I think we were up over 50 at one point in time. So it's great. It's been really, really successful. Thank you so much for answering all the student questions and from members of the public as well. It's really been a pleasure to have you guys all here, and so excited for Dragonfly. I was at AbSciCon when the mission was announced, and it was the most excited I have been, except for when we found out Europa Clipper was going to happen finally, and that our team got selected. So slightly selfish answer there, but it was amazing, and I'm so excited about it because I just think it represents everything that we should be doing. It's ambitious in every way, scientifically, engineering wise, but it also represents, something that I think is really important, which is the collaboration of engineering and science, which can often be a bit antagonistic in mission design processes. So I think it's really awesome, and it's the kind of thing that I think represents the frontier rather than the way we've always done business in the past. So congratulations to you guys as a team for accomplishing this really amazing work, and can't wait to see what's happening. And yeah, as Taylor was saying, we're all fangirling out here. So thank you very much for spending time with us today, and for making time for it. And best of luck. I'm sure you'll have lots of applications, not so distant future from folks that were on this call. So yeah,
thanks very much, Brittany, and thanks to everyone. I just wanted to thank for the great questions and discussion. We're really glad to be able to join you virtually, to have this conversation, and to be able to discuss so many wide-ranging aspects of the system that is Dragonfly. So thank you.
It's a perfect highlight. It is the perfect highlight because we have a mixture of engineering students and science students, and this semester's theme has been the mission process and instrument design and implementation as well, because that's the kind of things that you don't usually hear in your science presentations, and you don't in your engineering talks don't hear about how the engineering decisions and the science decisions play off each other to get this result. So it was great. Melissa, I think I cut you off. Sorry about that.
No, I was just saying it's been awesome, and I tried to help answer some more of the follow-up questions in the Q&A. Hopefully that helps clear up any lingering questions students have.
Awesome. Well, thanks everyone for an awesome semester. It's been a real pleasure. A reminder to feel free to register for the Planetary and Astrobiology seminar next semester. We're going to be highlighting probably a bit more astrobiology next time around. We'll kind of alternate back and forth because it's going to be held with the astrobiology seminal papers class. So let's kind of give everyone a hand and have a safe break, and take care of yourselves and your family. Thanks so much for coming and participating. So we'll talk to you guys all later.